Okay. Motion. Any motion that happens, I can actually think of it as a combination of linear motion and rotational motion. That is, for example, let's say I threw this hammer in the air, and the hammer was rotating like this as it flew through the air. Well, I can actually consider this the combination of this type of motion, which we call linear motion or translational motion, and then this type of motion. So if I combine this type of motion, rotational motion, with this type of motion, which is translational motion, then I get the motion of my object. And you can treat them separately, just like we used to treat the x and y components separately. You can also treat the linear part of the motion separately from the rotational part of the motion. So now, so essentially up till now, I've only been teaching you half of the story. Everything we did so far this year involved linear motion. Now we've got to do the rotational component of the motion. And that's what today's all about. We'll get you started on learning the rotational part of motion. So first things first, look at your Xerox. It says rotational motion. When an object rotates about an axis, every point on the object traces out a what kind of path? If this thing's rotating, imagine just a point on this hammerhead. As it rotates, what type of path is the hammerhead tracing out? How many people think it's circular? Yay, well that's what it is, circular. I don't know if I showed it that well, but it's circular. But when an object undergoes translational motion, the type that our kinematic equations apply to, every point on the object moves in what kind of lines? Like imagine the line that the bottom of the hammer, the middle of the hammer, and the top of the hammer is tracing out. What can you say about those lines? What's that? Okay, linear. Here, let me give you another example. Suppose I have this here. Here's my hammer. The black is the top of the hammer, the blue is the middle of the hammer, and the pink is the bottom, or maybe I'll go the opposite way. So the hammer flies through the air. Woo. What do you notice is true about those lines? Are you thinking they're parallel? Well, that's what they are. They're parallel. These are parallel lines. Okay? So that's the answer of that one. So with rotational motion, you get circles, and with linear motion, you get parallel lines. Okay. So now, it's time to teach you about the building blocks of rotational motion. And with translational motion, you had displacement, velocity, and acceleration. Well, with rotational motion, we get angular displacement, angular velocity, and angular acceleration. And let's go ahead and learn about each of those in turn. First, angular displacement. That's the angle that an object rotates through. We call it theta. The units are radians. Radians are unitless, defined by the equation theta equals s over r. Let me show you what I'm talking about with that. Theta. Imagine I have a circle. And imagine I have a central angle of the circle. That is an angle whose vertex is the center of the circle. And imagine the circle has a radius r, and that the central angle theta subtends an arc whose length is s. That is the linear length of that arc, not the angular measure of the arc, but the linear length of that arc is s. Then you supposedly learned in trigonometry, if you've had trigonometry, that we can define this angle theta in terms of the subtended arc length and the radius. And this angle theta is just the ratio of s over r. But the thing is, this definition of the angle theta is only good in radians. This is not the definition of this angle in degrees or any other measure. Only in radians is theta equal to s over r. You tell me, what's the units of this angle theta? Like, is it meters or seconds or kilograms? What's the units of the angle theta? What's that? Thank you very much. There's no units. It's unitless because arc length is measured in meters and radius is measured in meters, so it's going to be unitless. So I just want to remind you, theta in radians is a unitless quantity. So when we start dealing with omega, where the units of omega is radians per second, actually, you know, the units are 1/seconds because radians is a unitless quantity. But we still use radians because we want to, because it's cool. But I do want to let you know that radians has no units. Great. Tell me, look at the next line. 1 radian. If I had an angle of 1 radian, then what would the arc length S have to be equal to? What length must S have if the angle theta is going to be 1 radian? What's that?
R theta.
Yeah, R? Yeah, R. You guys okay with that? Theta, if I got 1 radian, then S is equal to R. So in that line there, just say an angle, subtends an arc of length 1 radius. Let's consider an angle theta that comprises an entire circle. Let's say my central angle isn't something that looks like 45 degrees. Let's say my central angle is the entire circle. So there's my angle theta, the entire circle. So that the subtended arc is the entire circumference. Well, theta equals S over R. How many radians is an entire circle going to be? Yeah, hopefully you're getting 2 pi. Because the subtended arc length is going to be the circumference 2 pi r. The radius is r. Okay? And so you end up with 2 pi. So I want you to see that an entire circle is 2 pi radians. You guys okay with that? So look at the conversion. 1 revolution. How many degrees is 1 revolution? 360. And how many radians?
2 pi.
Yeah, 2 pi. So write that in there. 360 degrees, 2 pi radians. Let's go ahead and do example number 1. Let's use this formula, theta equals S over R. I've got Earth. And I've got a satellite. And this satellite is 4.23 times 10 to the 7th meters away from the surface of the Earth. Oh, I'm sorry, away from the center of the Earth. This satellite is moving in a circular motion. And it just so happens the satellite moves through 2 degrees. And I want to know the distance that the satellite traveled. The satellite traveled. Well, I'm going to have to use this equation, theta equals S over R. Can I put 2 degrees for theta?
No.
Heck no. What am I going to have to convert that 2 degrees to?
Radian.
Yeah, I'm going to have to convert it to radians. So I'm going to have 2 degrees times. How many people here put 2 pi radians over 360 degrees? Good for you guys. How many people say pi radians over 180 degrees? That's fine too. However you like to do it is okay with me. I tend to do 2 pi over 360 just because that's kind of the conversion I learned. I don't know that I'm comfortable with. And this is going to equal S over the radius, which is 4.23 times 10 to the 7th meters. So I get a distance traveled of whatever the heck that is. 2 times 2 pi divided by 360 times 3 times 10 to the 7th So I got about 1.5 times 10 to the 6th meters. Okay. Here's the next issue. Example number 2. This is the issue of angular size. We humans do not see size, we don't see length, we see angular size, right? When I look at, let me think, how can I say this? When oh heck, we'll choose, I don't know who to choose. Normally I choose someone's head to smash, you know, I'm gonna go with Fatima's. When I choose Fatima's head to smash, okay, it would appear that her head is fitting right in between my 2 fingers. Does that mean her head has the same length as the space between my 2 fingers? No, of course not. But we don't see in length. We see an angular size. It so happens that the angular size of Fatima's head is the same as the angular size of my fingers. That is, when I'm here, and here's my eyeball, and I have my fingers separated, and I don't know how to draw 2 fingers, but I've got my fingers separated, and then here's Fatima's head, you know. It just so happens that the same angle that's in between my 2 fingers is the same angle that her head subtends. The arc that my fingers subtend is the same as her head subtends. And this is the idea of angular size. Sure, her head is not the same size as the space between my fingers, but the angular size of her head is the same as the angular size of the space between my 2 fingers. You see? And that's how we as human beings see. We see angular size. Any question or issue on that? And you've seen things like that where you've got a shot and there's a car and there's a man, and then the man walks to the car and then you realize the car was really just a little model car, but the car looked like a real car because at that moment on the camera the angular size of the car was such that it looked like it was bigger than the dude, so it looked like a real car. Have you ever seen that sort of thing? Okay, that's sort of trickery. Well, that's because we see angular size. So now let's go ahead and do example number 2, solar eclipse. Here's the situation. Let me erase Fatima there. So here's the Earth. Here's a human being standing on the Earth. And here's the moon. Okay? And I want to know what the angular size of the moon is. That is, what angle does the moon subtend in the person's sight? So, okay? So I want to know what this angle theta is. Well, the way I get that theta is to say, okay, I need to know the distance between the dude and the moon. I need to know this arc that's subtended by this angle, but we're going to say that this arc is approximately equal to the diameter of the moon. So that arc that's subtended, the S, is just going to be the diameter of the moon, because that's close enough for such a small angle. And then I can use theta equals S over R to find what the angle subtended by the moon is. Okay? Well, the S is the diameter of the moon, which is, just a second, 3.48 times 10 to the 6th meters. And then the lunar distance from the Earth is 3.85 times 10 to the 8th meters. Now, here's one little problem. One problem I have with my Xerox. Just a second. Thank you. So, oh, he is not here. I got the one guy who's absent. Yeah. Okay. All right, here's a weird thing. They tell me that the distance between the moon and the Earth is 3.85 times 10 to the 8th meters. That's this distance from the centers of mass is 3.85 times 10 to the 8 meters. Okay? But the problem is that's not the distance between the dude and the center of the moon. I'm going to have to subtract off 1 Earth radius, which is 6.38 times 10 to the 6th meters. So to get a really accurate measure, it's my mistake because I should have put it on the paper differently, but anyway, the distance between the dude and the moon is the lunar distance, 3.85 times 10 to the 8th meters, minus 1 Earth radius. So that we're getting the distance between the guy on the surface of the Earth and the moon. But anyway, this ends up being 0.00919 radians, just believe me. That's the angular size of the moon. And I think it turns out that if you held a penny in your hand and you held the penny at arm's length, then the angular size of that penny would be the same as the angular size of the moon. They both subtend the same arc. You know, if you held that penny right there, then the angular size of the penny would be the same as the angular size of the moon. Well, what comes next is I'd like you guys to find the angular size of the sun. Go ahead and do that now. And it'll be S over R. Now, those of you who understood why I had to subtract 1 Earth radius from the lunar distance, am I going to have to subtract 1 Earth radius from the solar distance? Well, I guess I should, but there's really a good reason why I don't have to. And why not? What is it about the solar distance that makes it that I don't really have to subtract 6.38 times 10 to the 6th from the solar distance? Yeah, Noel?
It's kind of negligible.
Yeah, it's really
like
negligible.
The Earth's radius.
Yeah, I mean, the solar distance is 10 to the 11th meters. It's 5 orders of magnitude greater than the solar radius, than the Earth radius, so don't go to the trouble. Just use the numbers I have there. So you guys getting about 0.00927 radii? Radians, I mean? I think that's what I get, isn't it? What's that? Do I have it on my calculator still? I don't know why I'm doing that, so I can just... I was going by memory, 1.39. .9, yeah, 927. Okay. So, what do you notice about, for us here on Earth, what do you notice about the angular size of the moon and the angular size of the sun?
Very identical.
Yeah, they're almost the same, right? Why does that make eclipses so cool? I mean, why does that make eclipses so cool, the fact that they have almost the same angular size?
Because the moon almost blacks out the sun.
Yeah, the moon just pretty much almost entirely blacks out the sun. Yeah, but what makes it cool is the angular size of the moon is actually ever so slightly smaller than the angular size of the sun. So you get your moon, and then you get your sun, and the sun is just slightly bigger than the moon. So you get this, and do you remember what do we call this part of the sun? It starts with the letter C. Yeah, the corona. You get the corona of the sun. So if there's any like solar flares that come out, you can see them really easily because the moon is essentially blocking all the light of the sun except for the corona. And so it's just a wonderful opportunity for us to study the sun that we wouldn't have if it didn't just so happen that we live in a solar system that the sun and the moon have the same angular size. So it's kind of cool that way. Yeah. And the fact that the moon's orbit passes through the solar plane so that we can actually have eclipses. It's really nice. We're lucky to live where we are in the universe. Okay. So anyway, hey, that's angular size, that's angular displacement. It is now time to talk about angular velocity. The letter for angular velocity, do I call it W? Heck no. If you call it W, people will look askance at you. People will doubt whether you are good at physics. Because what do we call the letter for angular velocity?
Omega.
Yeah, omega. It is the small letter omega. Capital omega looks like a horseshoe. Small omega looks like a W. Okay? There are many different units for angular velocity, not just radians per second. It could be revolutions per second, revolutions per minute, degrees per minute. Any of those sorts of measures is going to get you angular velocity. Well, look at example 3. I've got a gymnast that does 2 revolutions in 1.9 seconds. Find omega, find the angular velocity. What's going on? The camera's going crazy. It's flashing the light.
I think I fixed it.
Is it still recording?
Yeah.
Okay, cool. Yeah, it's funny when that light flashes. Okay, great. So I need omega in radians per second. Oh, I better hurry up here. Oh my gosh, we're almost out of time. We're like 8 minutes left. Okay, here we go. Zip-dee-doo-dah. Omega. I got 2 revolutions in 1.9 seconds. But you know we don't want revolutions per second, we want radians per second. So I'm going to go, okay, I got 2 pi radians in 1 revolution. Are you guys okay with that? 2 pi radians is 1 revolution. So this ends up being 4 pi divided by 1.9. So I got 6.6 radians per second. Here, let's look at example number 4. Please turn the page. Is that okay with you guys?
Yeah.
Okay. Angular acceleration, we call it alpha. The units of alpha are radians per second per second. It can be other units as well, but we most always use radians per second or radians per second squared. So look at example number 4. I want my average angular acceleration. Well, that's going to be the change in omega over the change in time, right? My turntable goes from rest to 45 RPM. So the change in omega is 45 RPM. 45 RPM minus 0. And the amount of time I do it in is 3 seconds. So are you okay? I've got 15 RPM per second. And that's good. That's a measure of angular acceleration, revolutions per minute per second. If you had an automobile, that's probably the way you would measure angular acceleration. An engine that's revving from 0 to 5,000 RPM in 6 seconds, you would like to have it be 833 RPM per second. But let's say I wanted to convert this into radians per second squared. Any question or problem on this? Okay? I'm just seeing concern. Well, anyway, radians per second, I would do this. This is 15 revolutions per minute per second. And you'll notice the revolutions per minute is entirely in the numerator. So I'd want you to do your conversion just in the numerator. So I've got the 2 pi radians in 1 revolution. And I've got 1 minute in 60 seconds. And now I've got my radians per second, because I've just converted the 15 revolutions per minute into radians per second. So I got 15 times 2 times pi divided by 60, about 1.6. 1.6 radians per second squared. So now that you guys are supposedly good with angular displacement, angular velocity, and angular acceleration, we now can do the rotational kinematic equations. That light is on. Here, did you press this button? Here, just a second. Light. Wait. Boop. Wait, I thought that was. There we go. Is that good?
Yeah.
All righty. Unless you think I need light.
No. Just
Maybe
right
I need
now.
some makeup too. Okay. Rotational kinematics. Just as we have 4 kinematic equations for linear motion when the is constant, tell me those 4 kinematic equations when the is constant. What time is this class over? 23. So we're almost done. Wow, I did not get through the rotational kinematic equations. Well, we'll just have to, we'll start it with it tomorrow. I don't know where the time went. That's so weird. Okay, well, we'll just stop here, and I think you'll be fine on tonight's homework. Bye-bye.